before you fall asleep tonight, imagine this. The light reaching your eyes began its journey billions of years ago. Tiny particles from distant stars pass silently through your body right now. Invisible structures guide galaxies across the universe, shaping everything you see and everything you never notice. Tonight, we'll drift through the quiet forces that built the cosmos, from the universe's first light to the hidden currents still moving through space today. Let the noise fade. Let the universe speak softly. And allow your mind to rest among the stars. Hello, and welcome to Dreamy Science Stories. I'm truly glad you've arrived here tonight. Wherever you are listening from, allow this moment to belong entirely to you. Let the outside world slowly fade into the background. Let distant worries soften, like echoes dissolving into the night. As your breathing becomes calm and steady, imagine yourself gently floating upward, leaving behind the weight of the day. Picture the sky opening above you. A vast, silent ocean of darkness, scattered with light. Tonight, we'll drift together through the cosmos, gliding past hidden worlds, glowing stars, and galaxies so ancient their light began its journey long before Earth existed. We'll explore quiet truths about the universe, its immensity, its mysteries, and the invisible threads that connect everything you have ever known. Some of these ideas may awaken your curiosity. Others may settle gently into your mind, like starlight resting on still water. If these calm explorations bring you comfort or wonder, you're welcome to like or subscribe, helping other sleepy travelers find their way here as well. But for now, there is nowhere else you need to be. Get comfortable. Our journey through the universe begins. When you look up at the night sky, the stars may seem countless. But their true number is almost impossible to grasp. Scientists estimate that there are more stars in the universe than grains of sand across all the beaches on Earth. Every shoreline, every desert, every drifting grain combined still falls short of the cosmic total. Each of those stars is a massive sphere of glowing plasma, many far larger or smaller than our own sun. Some may host planets. Some may shine alone in the dark. Together, they form an unimaginably vast tapestry of light stretching across space and time. This abundance reminds us that the universe is not sparse or empty, but overflowing with structure, energy, and possibility. A silent ocean of brilliance extending far beyond the reach of human thought. The part of the universe we can observe spans about 93 billion light-years across. This is the visible universe, containing all the galaxies whose light has had enough time to reach us since the beginning of time itself. But this immense expanse may be only a fraction of what truly exists. Beyond this cosmic horizon, space may continue endlessly, filled with stars and galaxies forever hidden from view. Their light has not yet arrived. Perhaps it never will. This boundary is not a physical edge, but a limit to perception, a reminder that much of reality exists beyond our ability to see or measure. The universe holds more than it reveals, resting quietly beyond the reach of our instruments and imagination. Space itself is expanding. Galaxies are not simply drifting through empty space. They are being carried apart as space stretches between them. Imagine small dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from one another, not because they are moving on their own, but because the surface beneath them is growing. This expansion affects the entire universe. Over time, galaxies grow more distant, light takes longer to travel, and the shape of the cosmos slowly changes. This gentle but relentless stretching has been happening for billions of years, shaping the universe on its grandest scales, quietly guiding the future of space and time. The Big Bang was not an explosion in space. It was the birth of space and time themselves. Before the Big Bang, There was no place for matter to exist and no time for events to unfold. From a state of unimaginable density and heat, the universe began expanding everywhere at once. Space came into being. Time began to flow. Energy cooled, particles formed, and eventually stars and galaxies emerged. This moment was not a blast outward into emptiness. It was the creation of the stage upon which all existence would unfold. A beginning so profound that it reshaped the meaning of origin itself. Even now, ancient light from those earliest moments still surrounds us. The cosmic microwave background is a faint glow filling all of space, a quiet afterimage of the young universe. This radiation has been traveling for nearly 14 billion years, ever since the cosmos cooled enough for light to move freely. It is the oldest light we can observe, a snapshot of the universe as it once was. Within this subtle glow lie tiny variations, the seeds from which galaxies eventually grew. It is a silent messenger from the dawn of time, whispering the story of creation in every direction. Much of the universe is shaped by something we cannot see. Dark matter makes up the vast majority of the universe's matter, yet it emits no light and interacts only through gravity. It forms an invisible framework that holds galaxies together, preventing them from flying apart as they spin. Without dark matter, stars would drift away, and galaxies would unravel. Though unseen, its influence is profound, guiding the formation of cosmic structures and shaping the universe's vast web. The invisible, it seems, often holds the greatest power. Even more mysterious is dark energy, a force pushing the universe to expand faster and faster. Once thought to be slowing down, the expansion of the universe was discovered to be accelerating. Dark energy, which makes up most of the universe's total energy, acts like a gentle but unstoppable pressure, driving galaxies apart. Its nature remains unknown. It challenges our understanding of physics and forces us to reconsider the ultimate fate of the cosmos. Whether the universe will expand forever or end in some distant transformation remains one of the deepest unanswered questions. Galaxies themselves are not scattered at random. They are woven into a vast cosmic web, connected by filaments of dark matter stretching across hundreds of millions of light-years. Along these threads, galaxies cluster and grow. Between them lie enormous voids, regions of near emptiness. This delicate structure governs how galaxies evolve, interact, and change over time. Though invisible to our eyes, the cosmic web binds the universe together in an intricate and ancient design. Our own galaxy, the Milky Way, is part of this grand motion. It spins at over 500,000 miles per hour, carrying our solar system along for the ride. Once every 250 million years, we complete a single orbit around the galactic center. During this journey, we pass through spiral arms, star-forming regions, and clouds of cosmic dust. Despite the incredible speed, the vast distances between stars keep collisions rare. This quiet motion reminds us that we are travelers in a living galaxy, moving through space on a journey far older than humanity itself. Sometimes, galaxies meet. When they do, gravity draws them into slow, majestic dances lasting billions of years. Their shapes stretch and twist. Gas clouds collapse into new stars. Central black holes grow and shine. Our own Milky Way is destined to merge with the nearby Andromeda galaxy in about 4 billion years. When it happens, the night sky will transform, stars filling the heavens in new patterns, as two cosmic cities become one. In the distant universe, quasars shine like beacons from the past. Powered by supermassive black holes feeding on surrounding matter, quasars release staggering amounts of energy, outshining entire galaxies. Their light travels across billions of light-years, allowing us to peer back into the universe's earliest eras. Through them, we glimpse the growth of black holes and the formation of young galaxies, reminders that even the darkest objects can illuminate the cosmos. As this journey slowly settles, allow your thoughts to drift like galaxies through space. Let the immensity of the universe cradle you rather than overwhelm you. You are part of this vast story, made of the same matter, moving through the same cosmic rhythm. If your eyes feel heavy now, that's perfectly okay. Let them close. Let the universe continue its quiet motion around you. Sleep gently, and let the stars keep watch. A vast sea of ancient neutrinos still fills the universe today. These relic particles were released within the first second after the Big Bang and have been streaming freely through space ever since. Known as the cosmic neutrino background, they carry information from an era even earlier than the oldest light we can observe. Unlike photons, neutrinos pass through nearly everything, making them extraordinarily difficult to detect. Yet their subtle influence affects how galaxies and large-scale structures form. Unlocking their secrets could reveal unprecedented insight into the universe's earliest moments. The rate at which the universe expands is described by a value called the Hubble constant. This number links a galaxy's distance from us to how fast it is moving away. Measuring it accurately is crucial for determining the universe's age, size, and fate. Yet different measurement methods produce slightly different results, a puzzle known as the Hubble tension. Resolving this discrepancy may lead to new physics and deeper understanding of cosmic expansion. The Hubble constant remains a central anchor in our exploration of the universe's history. As galaxies move away from us, the light they emit stretches into longer, redder wavelengths, a phenomenon known as redshift. This effect is similar to how a siren's pitch lowers as it moves away. Redshift provides direct evidence that the universe is expanding and allows astronomers to measure cosmic distances and look back in time. By studying redshift, scientists can reconstruct how the universe has grown and changed over billions of years, tracing the slow unfolding of cosmic history. To measure the vast distances of space, astronomers rely on a method called the cosmic distance ladder. Because no single technique works at all scales, scientists build measurements step by step. Nearby stars are measured using parallax, while more distant objects rely on standard candles such as Cepheid variables and supernovae. Each rung of the ladder builds upon the previous one, allowing astronomers to map the universe with increasing precision. This careful process helps reveal the true scale of cosmic structures and the timeline of cosmic evolution. There is a limit to how far we can see. This boundary is known as the cosmic horizon. Because the universe has a finite age, light from beyond a certain distance has not yet had time to reach us. The cosmic horizon defines the observable universe, a vast sphere containing everything we can detect. Beyond it may lie countless galaxies and realms forever hidden from view. As time passes, this horizon slowly expands, revealing more of the cosmos. Yet it also reminds us that some mysteries will always remain beyond reach, inviting humility, curiosity, and quiet wonder as we drift beneath the stars. Quasars act like cosmic lighthouses, shining across unimaginable distances and illuminating the deep, intergalactic darkness. Their light travels for billions of years, revealing what the universe was like in its earliest youth. Powered by supermassive black holes consuming vast amounts of matter, quasars release staggering energy, often outshining entire galaxies. Because of their immense brightness and extreme distance, they allow astronomers to peer farther back in time than almost any other object. To observe a quasar is to witness a beacon from the ancient universe, still whispering stories of its turbulent beginnings across the quiet sea of space. In the very first moments after the Big Bang, the universe experienced an astonishing event known as cosmic inflation. In a tiny fraction of a second, space itself expanded exponentially, stretching faster than the speed of light. This was not matter moving through space, but space itself rapidly growing. Inflation smoothed out irregularities, explaining why the universe appears remarkably uniform on large scales today. At the same time, tiny quantum fluctuations were stretched into vast structures, becoming the seeds of galaxies and cosmic filaments. Inflation remains a cornerstone of modern cosmology, offering deep insight into how the universe began and why it looks the way it does now. For hundreds of millions of years after the Big Bang, the universe existed in darkness. No stars had yet formed, and space was filled with cold, neutral gas. Then, the first stars ignited. Massive, brilliant, and short-lived, they pierced the cosmic night for the very first time. These ancient stars burned intensely, forging the first heavy elements within their cores. Their radiation transformed the surrounding hydrogen, gradually making the universe transparent to light. This era, known as cosmic dawn, marked a turning point when darkness gave way to illumination, setting the stage for galaxies, planets, and eventually life itself. High-energy particles known as cosmic rays raced through space at nearly the speed of light. Born from violent cosmic events such as supernova explosions and energetic black holes, these charged particles are flung across the universe with immense force. When cosmic rays reach Earth, they collide with atoms in our atmosphere, creating cascades of secondary particles that rain down invisibly around us. Though we cannot feel them, these energetic travelers subtly influence atmospheric chemistry and may even play a role in cloud formation. Cosmic rays serve as a quiet connection between our planet and the universe's most extreme events. Our home galaxy does not exist in isolation. The Milky Way belongs to an enormous structure known as the Laniakea supercluster, a vast gravitational community containing thousands of galaxies. Spanning hundreds of millions of light-years, this immense cosmic region draws galaxies together into slow, collective motion. Within this supercluster, galaxies interact, merge, and evolve under the influence of shared gravity. Understanding our place within Laniakea helps astronomers comprehend how matter is organized on the largest scales and how the universe's grand architecture is shaped. Between clusters of galaxies lie immense regions called cosmic voids. These vast expanses contain very little matter and few galaxies, stretching across tens of millions of light-years. Though they may seem empty, voids still contain faint gas and dark matter, quietly influencing the motion of surrounding galaxies. Their presence sculpts the cosmic web, shaping how matter clumps and spreads across space. Studying these voids offers valuable clues about dark energy, matter distribution, and the large-scale evolution of the universe. Nearly invisible particles called neutrinos pass through everything, including your own body, every moment of every day. Created in vast numbers by the Sun, supernovae, and distant cosmic processes, neutrinos barely interact with matter at all. Trillions of them pass through you each second without leaving a trace. Detecting them requires enormous, sensitive instruments buried deep underground or beneath Antarctic ice. Though elusive, neutrinos carry precious information about stellar explosions, the inner workings of stars, and the fundamental laws of physics, quietly linking us to the universe's most energetic events. When viewed on the largest possible scales, the universe appears remarkably uniform. No matter which direction we look, galaxies are distributed in a similar way, with no preferred center or edge. This property, known as cosmic isotropy and homogeneity, forms a foundational assumption of modern cosmology. Observations of the cosmic microwave background strongly support this idea, revealing a universe that looks much the same everywhere when seen from a sufficiently grand perspective. This surprising uniformity hints at deep symmetries woven into the fabric of existence. Tiny grains of cosmic dust drift silently through space, yet they play a role far greater than their size suggests. These microscopic particles, made of carbon, silicon, and trace metals, float within vast clouds of gas scattered across the universe. Though almost invisible, cosmic dust is essential to creation itself. Inside dense nebulae, dust grains help radiate heat away, allowing clouds to cool and collapse under gravity. This quiet cooling process gives birth to new stars. Around young stars, dust particles gently collide and cling together, slowly forming pebbles, then rocks, and eventually planets and moons. Dust also provides surfaces where complex molecules can assemble, nurturing the chemistry that may one day lead to life. In this way, the universe builds its grand structures from the smallest fragments, shaping worlds grain by grain. The universe's very first stars were strikingly simple in composition. Formed from primordial clouds almost entirely made of hydrogen and helium, these ancient stars contained none of the heavier elements we see today. Known as the earliest stellar populations, they burned intensely hot and lived brief, luminous lives. Their immense mass caused them to exhaust their fuel quickly, ending in colossal supernova explosions. In these final moments, they forged and scattered the first heavier elements such as carbon, oxygen, and iron into the surrounding space. Though these original stars no longer exist, their explosive deaths transformed the universe, seeding it with the materials required for future stars, planets, and eventually life itself. Hidden behind thick veils of cosmic dust, distant galaxies shine brightly in infrared light. To optical telescopes, these galaxies may appear dark or invisible, their visible light absorbed by dust clouds. Yet this same dust glows warmly in infrared wavelengths after absorbing energy from intense star formation within. By observing the universe in infrared, astronomers can peer through these dusty curtains and witness regions where stars are forming at extraordinary rates. These dusty star-forming galaxies reveal crucial chapters in the story of galaxy growth, helping scientists understand how the universe evolved during its most active eras. Cosmic rays, high-energy particles born in distant cosmic violence, constantly rain down upon Earth. Accelerated by supernova explosions and powerful black holes, these fast-moving particles strike our atmosphere, triggering cascades of secondary particles. Some researchers suggest that this atmospheric ionization may influence cloud formation, subtly shaping weather and climate patterns. Though the extent of this influence remains under study, cosmic rays represent a quiet connection between the far reaches of space and the delicate systems of our own planet. Even the weather above us may carry faint echoes of distant stellar catastrophes. The universe is overwhelmingly made of matter, yet this fact presents one of science's greatest mysteries. According to theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated one another completely. And yet, matter prevailed. This imbalance, known as baryon asymmetry, allowed galaxies, stars, and life itself to exist. Why matter survived while antimatter nearly vanished remains unknown. Solving this mystery could explain why the universe exists in its current form, making it one of the most profound unanswered questions in cosmology. Gravity leaves delicate fingerprints on the oldest light in the universe. As ancient light travels across space, it passes near massive objects whose gravity gently bends and distorts its path. This effect, known as gravitational lensing, subtly warps the cosmic microwave background, the faint afterglow of the Big Bang. By studying these distortions, astronomers can map the distribution of both visible and invisible matter, revealing the hidden structure of the cosmos. Gravity, though unseen, quietly reshapes the light that reaches us from the depths of time. Light traveling through the universe is never entirely untouched. Massive galaxy clusters and black holes bend and stretch the paths of passing light, magnifying distant objects and sometimes splitting them into arcs or rings. This gravitational lensing acts as a natural telescope, allowing astronomers to observe galaxies far beyond the reach of conventional instruments. Through these warped images, scientists can also detect dark matter, which reveals itself only through gravity. In this way, bent light becomes a guide to understanding the universe's invisible foundations. After a long era of darkness, the universe's first light finally emerged. Hundreds of millions of years after the Big Bang, the first stars and galaxies ignited, bringing an end to the cosmic dark ages. Their combined glow illuminated space for the first time, transforming the universe from a shadowed expanse into a luminous realm. This ancient light marked the beginning of structure, motion, and complexity on a cosmic scale. It was the universe's first awakening, setting the stage for everything that would follow. In its early years, the universe was filled with a dense fog of neutral hydrogen gas. Light struggled to travel freely through this opaque medium. But as the first stars and galaxies formed, their ultraviolet radiation ionized the hydrogen, stripping electrons from atoms and clearing the cosmic fog. This era of reionization allowed light to stream across vast distances, making the universe transparent. From this moment onward, the large-scale cosmic web became visible, and the universe began to shine openly across space and time. Billions of years ago, the universe reached a period of extraordinary productivity often called cosmic high noon. During this era, galaxies formed stars at a furious pace, far exceeding today's rates. This surge enriched the universe with heavy elements and laid the foundations for planets and life. Over time, star formation slowed, and the cosmos entered a calmer phase. Yet the legacy of this golden age remains woven into every galaxy, solar system, and living world. As stars lived and died, the universe grew increasingly complex. Early on, hydrogen and helium dominated, but stellar fusion gradually created heavier elements within stellar cores. When massive stars exploded, these elements were scattered into space, enriching future generations of stars and planets. This cosmic recycling transformed the universe from a simple beginning into a chemically diverse environment capable of supporting life. Every atom in your body carries the memory of stars long gone. On the largest scales, matter in the universe forms a vast cosmic web. Giant filaments of dark matter and gas connect clusters of galaxies across millions of light-years, while enormous voids lie between them. This structure guides the movement of galaxies and shapes their evolution. Mapping this web reveals the hidden framework of the cosmos, showing that the universe is not random, but intricately connected. At the hearts of many galaxies, supermassive black holes unleash powerful jets of particles. These jets shoot outward at near-light speed, stretching for millions of light-years and influencing their surroundings. By heating and dispersing gas, they regulate star formation and shape the growth of galaxies. Though born from darkness, these jets play a vital role in the universe's balance, demonstrating how even the most extreme forces contribute to cosmic harmony. By observing these powerful jets, astronomers uncover the dynamic relationship between black holes and their surrounding cosmic environments. These streams of energy reveal how black holes are not merely destructive forces, but active participants in shaping galaxies. As jets carve through intergalactic space, they redistribute matter and energy, influencing star formation and galactic growth. They stand as some of the universe's most dramatic expressions of balance between gravity and motion. Massive galaxy clusters form the densest gathering points within the cosmic web. These colossal structures contain hundreds or even thousands of galaxies bound together by gravity, spanning regions millions of light-years wide. Acting as the universe's great meeting places, clusters anchor the vast filaments of dark matter and gas that weave through space. Within them, galaxies interact, merge, and evolve, while enormous clouds of superheated gas glow brightly in X-rays. Studying galaxy clusters allows scientists to trace the distribution of matter on the largest scales and uncover clues about dark matter, dark energy, and the universe's long-term evolution. Measurements show that the universe's overall shape is astonishingly close to flat. Unlike a sphere that curves inward or a saddle that bends outward, a flat universe follows precise geometric balance. In such a cosmos, parallel lines remain parallel even across immense distances, shaping how light travels and how structures form. This remarkable flatness supports theories of cosmic inflation and suggests the universe will continue expanding indefinitely rather than collapsing back in on itself. Understanding the universe's geometry helps reveal both its origins and its ultimate fate. Tiny temperature differences imprinted on ancient light became the seeds of all cosmic structure. The cosmic microwave background appears smooth at first glance, yet it contains minute variations only millionths of a degree apart. These subtle ripples represent tiny density differences in the early universe. Over billions of years, gravity amplified these slight imbalances, drawing matter together to form galaxies, clusters, and the vast cosmic web. These fluctuations act as the universe's original blueprint, preserving a record of how everything we see today began. Some uncertainty in cosmological measurements arises simply because we observe only one universe. This limitation, known as cosmic variance, means scientists must interpret data from a single cosmic realization. Without multiple universes for comparison, it is difficult to determine whether observed patterns are universal or coincidental. As a result, astronomers rely on advanced statistical methods and careful modeling to draw reliable conclusions. Cosmic variance reminds us that even with powerful tools, our knowledge of the universe is shaped by perspective and limitation. Scientists reconstruct cosmic history by measuring the ages of distant galaxies. Because light takes time to travel, observing faraway galaxies allows astronomers to see them as they existed billions of years ago. By analyzing stellar populations and spectral signatures, researchers estimate when stars formed and how galaxies evolved over time. These age measurements help build a timeline of cosmic events, revealing how structure, chemistry, and complexity gradually emerged across epochs. Some theories suggest that cosmic strings may be relics from the universe's earliest moments. These hypothetical structures are imagined as ultra-thin, immensely dense filaments formed during phase transitions shortly after the Big Bang. If they exist, cosmic strings could leave subtle imprints on space-time, producing gravitational waves or distortions in ancient light. Though no direct evidence has yet been found, the possibility of cosmic strings offers a fascinating bridge between quantum physics and cosmology. Powerful X-rays glow from distant black holes as they devour surrounding matter. When gas and dust spiral into supermassive black holes, they form intensely heated accretion disks where temperatures reach millions of degrees. This extreme environment produces brilliant X-rays detectable across billions of light-years. These signals reveal violent processes near the event horizon and help scientists understand how black holes grow and influence their host galaxies. Each X-ray beacon acts as a distant signal from one of the universe's most extreme environments. Within galaxies, turbulent clouds of gas quietly shape the birth of stars. Gravity, shockwaves from supernovae, and magnetic forces stir these clouds into chaotic motion. In some regions, turbulence compresses gas until dense pockets collapse, igniting new stars. The balance between turbulence and gravity determines how many stars form and how massive they become. This ongoing interplay governs the life cycle of galaxies, turning disorder into creation. Radio waves from pulsars and distant galaxies fill the universe with invisible signals. Pulsars, rapidly spinning neutron stars, sweep beams of radio energy across space like cosmic lighthouses. At the same time, galaxies emit radio waves from star formation, magnetic fields, and black hole jets. Radio astronomy allows scientists to study these hidden signals, revealing structures and processes invisible to the human eye. Together, these waves form a quiet cosmic symphony echoing through space. Exploding stars launch particles that race through space as cosmic rays. When massive stars collapse in supernova explosions, they generate shock waves capable of accelerating particles to near-light speed. These cosmic rays travel across the galaxy, occasionally striking Earth's atmosphere and producing detectable cascades of secondary particles. They serve as messengers from distant, violent events, linking our planet to the broader dynamics of the universe. Patterns in the polarization of ancient light reveal clues about the universe's earliest moments. The cosmic microwave background is not only faintly glowing but subtly polarized, carrying information about density fluctuations and gravitational waves from the dawn of time. By studying these patterns, scientists test theories of inflation and gain insight into how tiny quantum ripples grew into galaxies and clusters. These delicate signals offer one of the clearest windows into the universe's birth. Ultraviolet radiation from the first stars transformed the universe from opaque to transparent. Early space was filled with neutral hydrogen that absorbed light, creating a cosmic fog. As stars ignited, their ultraviolet radiation ionized this gas, stripping electrons from atoms and clearing the fog. This process, known as reionization, allowed light to travel freely across the cosmos. From that moment on, the universe became visible, revealing the vast structures we observe today. Reionization marks one of the most important turning points in cosmic history, opening the universe's windows and guiding its transformation toward the star-filled sky we see today. As the universe slowly emerged from primordial darkness, the very first galaxies ignited brilliant ultraviolet light. This intense radiation ionized the surrounding hydrogen gas, stripping electrons from atoms and fundamentally altering the nature of space. What was once a dense, light-blocking cosmic fog became a transparent universe where photons could travel freely for the first time. This transition allowed light to spread across immense distances, revealing the growing web of galaxies and large-scale structure. By studying reionization, scientists gain insight into how the earliest luminous objects reshaped the universe and laid the foundation for everything that followed. Dark energy's mysterious influence is driving the universe to expand faster and faster. While gravity works to pull matter together, observations revealed a surprising truth: cosmic expansion is accelerating. This acceleration is attributed to dark energy, an unknown form of energy that permeates space and acts like a repulsive force. Accounting for roughly 70% of the universe's total energy content, dark energy dominates the cosmos while remaining deeply mysterious. Its origin, nature, and long-term impact are among the greatest unanswered questions in science. Whether dark energy will lead to endless expansion or an entirely different cosmic destiny remains unknown, making it a central focus of modern cosmology. The scale factor provides a simple yet powerful way to describe how the universe expands over time. Cosmologists use this dimensionless number to track how distances between galaxies grow as space itself stretches. When the scale factor increases, galaxies move farther apart, not because they are traveling through space, but because space is expanding between them. By measuring how the scale factor changes throughout cosmic history, scientists can reconstruct the universe's expansion rate and understand the influence of dark energy. This concept allows researchers to chart the gradual unfolding of the cosmos across billions of years. The curvature of the universe plays a key role in determining its overall shape and long-term fate. Depending on the total amount of matter and energy, the universe may be flat, open, or closed. In a flat universe, parallel lines remain parallel across vast distances, indicating a delicate balance between gravity and expansion. A closed universe would curve like a sphere and might eventually collapse, while an open universe would expand forever. Current observations reveal that the universe is astonishingly close to perfectly flat. This geometry shapes how light travels, how structures form, and how the universe will continue its cosmic journey. On the largest scales imaginable, matter in the universe is distributed remarkably evenly. When viewed across hundreds of millions of light-years, galaxies and dark matter appear statistically uniform, with no region significantly denser or emptier than another. This large-scale homogeneity supports the cosmological principle, which assumes that the universe is both uniform and isotropic when viewed broadly enough. While smaller regions contain clusters, filaments, and voids, the overall balance reveals deep symmetries that guide cosmic evolution. The universe also appears nearly the same in every direction we observe. This property, known as cosmic isotropy, means that the cosmos looks uniform regardless of where we point our instruments. Measurements of the cosmic microwave background show an almost identical temperature across the sky, reinforcing this idea. Together, isotropy and homogeneity form the foundation of modern cosmology, allowing scientists to build universal models that describe the universe's history, expansion, and structure with remarkable precision. The discovery of cosmic microwave background radiation provided decisive evidence for the Big Bang. In 1965, scientists Arno Penzias and Robert Wilson unexpectedly detected a faint microwave signal coming uniformly from all directions in space. This radiation was later identified as the afterglow of the Big Bang, dating back nearly 14 billion years to the moment the universe first became transparent. Detailed studies of this ancient light revealed tiny temperature variations that seeded the formation of galaxies and cosmic structures. The cosmic microwave background remains one of the most important observational pillars of cosmology, preserving a snapshot of the universe in its infancy. Cosmic history spans an extraordinary range of time, from fractions of a second to billions of years. The universe began in the Planck epoch, an unimaginably brief instant following the Big Bang. From there, it passed through dramatic stages such as inflation, recombination, cosmic dawn, and galaxy formation. Space expanded, matter cooled, light emerged, and structure slowly took shape. Over billions of years, galaxies matured, stars ignited, and planets formed. This immense timeline reveals a universe in constant transformation, where every era builds upon the last in an ongoing cosmic story. The observable universe continues to grow as the cosmic light horizon expands. This horizon marks the greatest distance from which light has had time to reach us since the Big Bang. As the universe ages, this boundary slowly moves outward, allowing us to see increasingly distant galaxies. Yet, due to accelerating expansion, some regions may remain forever beyond our reach. The cosmic horizon defines the limits of observation, reminding us that even as knowledge expands, vast portions of the universe remain hidden. Brief yet immensely powerful flashes of energy occasionally illuminate the universe. Gamma-ray bursts are intense eruptions of high-energy radiation that can briefly outshine entire galaxies. Lasting from milliseconds to minutes, these events often result from collapsing massive stars or merging neutron stars. Despite their fleeting nature, gamma-ray bursts release extraordinary amounts of energy and can be detected across the observable universe. They act as cosmic beacons, offering clues about stellar death, black hole formation, and extreme physics. As space expands, the light traveling through it is stretched. This effect, known as cosmological redshift, increases the wavelength of light, shifting it toward the red end of the spectrum. Distant galaxies appear redder not because of motion through space alone, but because space itself has expanded during the light's journey. Redshift serves as a crucial tool for measuring cosmic distances and expansion rates, allowing astronomers to look deep into the universe's past. Relic neutrinos have filled the universe since its earliest moments. Within the first second after the Big Bang, these nearly massless particles decoupled from matter and began streaming freely through space. Although extremely difficult to detect due to their weak interactions, relic neutrinos influence cosmic evolution and structure formation. They represent a fossil record of the early universe, carrying information from a time far earlier than light itself can reveal. Cosmic voids are vast regions of near emptiness separating galaxy clusters and filaments. Stretching across millions of light-years, these enormous spaces contain very little matter. Though seemingly empty, cosmic voids play a crucial role in shaping the large-scale structure of the universe, outlining the web-like pattern formed by galaxies and dark matter. Their silent presence highlights the contrast between matter and emptiness, completing the grand architecture of the cosmos. These immense cosmic voids resemble vast deserts in space, standing in striking contrast to the dense clusters of galaxies and glowing filaments that surround them. Although they contain very little matter, these empty regions play an essential role in shaping the universe's large-scale structure. Their gravitational influence affects how nearby galaxies move and cluster, subtly guiding the flow of matter across cosmic distances. By studying voids, scientists gain valuable insight into the distribution of dark matter, the influence of dark energy, and the overall evolution of cosmic architecture. These quiet expanses highlight the universe's immense scale and the delicate balance between matter and emptiness. Galaxies grow larger and more complex through slow, graceful mergers that unfold over billions of years. Rather than remaining static, galaxies are constantly evolving as they interact and combine with their neighbors. During these mergers, stars, gas, and dark matter gradually blend together, reshaping galactic structures. Such encounters can ignite bursts of star formation and funnel material toward central black holes, fueling their growth. Our own Milky Way is destined to merge with the Andromeda Galaxy in several billion years, forming a single, larger system. These cosmic unions reveal how the universe builds complexity over immense spans of time. Invisible magnetic fields weave through galaxies, quietly guiding charged particles and shaping cosmic environments. Though far weaker than Earth's magnetic field, galactic magnetic fields extend across thousands of light-years, threading through spiral arms and surrounding halos. They influence the movement of cosmic rays, affect the behavior of interstellar gas, and play a role in regulating star formation. By studying these unseen forces, astronomers uncover how energy and matter interact on vast scales. These magnetic threads add another hidden layer to the universe's intricate design. Cosmic rays occasionally leave subtle marks on life here on Earth. Originating from powerful events such as supernova explosions, These high-energy particles travel across the galaxy and collide with Earth's atmosphere. The resulting cascades of secondary particles can reach the planet's surface, sometimes interacting with living cells. In rare cases, they may cause changes in DNA, contributing to genetic variation over long timescales. While most effects are harmless, this constant cosmic rain illustrates how events far beyond Earth can gently influence the story of life on our planet. In the universe's earliest moments, dramatic phase transitions may have shaped space itself. As the cosmos rapidly cooled after the Big Bang, fundamental forces separated and symmetries broke, possibly creating bubble-like structures in space-time. These expanding and colliding bubbles could have left subtle imprints in the cosmic microwave background or generated faint gravitational waves. Detecting such signals would offer a rare glimpse into high-energy physics and the conditions of the infant universe, revealing traces of its fiery beginnings. Tiny fluctuations preserved in ancient light reveal how the universe began. The cosmic microwave background contains minute variations in temperature and density, representing slight differences in matter distribution shortly after the Big Bang. Over billions of years, gravity amplified these small irregularities, giving rise to galaxies, clusters, and vast cosmic filaments. By mapping these fluctuations with extraordinary precision, scientists reconstruct the universe's earliest conditions and test fundamental cosmological theories. These delicate patterns serve as a cosmic blueprint for everything we observe today. Cosmic rays also contribute to one of Earth's most beautiful natural displays, the northern and southern lights. When energetic particles interact with Earth's magnetic field near the poles, they collide with atmospheric gases, causing them to glow in vibrant shades of green, red, and purple. Alongside particles from the solar wind, cosmic rays energize the upper atmosphere, creating shimmering auroras. These luminous curtains remind us that Earth's skies are connected to distant cosmic events. Galaxies move along invisible gravitational pathways shaped by the universe's matter distribution. Rather than drifting randomly, galaxies follow large-scale flows defined primarily by dark matter. These gravitational currents guide galaxies along filaments of the cosmic web, drawing them toward massive clusters while skirting vast voids. This slow cosmic motion influences how galaxies interact, merge, and evolve. By tracing these flows, astronomers map the hidden structure of the universe and uncover the forces driving its long-term evolution. Roughly 380,000 years after the Big Bang, light was finally free to travel across the universe. As the cosmos cooled, electrons combined with protons to form neutral atoms in a process called recombination. This change allowed photons to decouple from matter and move unhindered through space. The light released during this moment is observed today as the cosmic microwave background. Studying this ancient glow provides a direct window into the universe's early conditions and the beginnings of cosmic structure. Small temperature variations in this ancient light became the seeds of galaxies and clusters. Though the cosmic microwave background appears nearly uniform, it contains tiny fluctuations only a few millionths of a degree in size. These variations correspond to early density differences that gravity gradually amplified. Over billions of years, matter clumped together, forming galaxies, clusters, and the vast cosmic web. Mapping these subtle temperature patterns allows scientists to peer into the universe's infancy and understand how structure emerged from near uniformity. Gravitational tides slowly stretch and reshape galaxies over time. Just as the moon's gravity creates tides on Earth, the gravitational pull of neighboring galaxies and dark matter exerts tidal forces on galactic structures. These forces can distort spiral arms, trigger waves of star formation, and sometimes lead to dramatic mergers. Over immense timescales, tidal interactions play a crucial role in shaping galaxies and driving their evolution within crowded cosmic neighborhoods. During the brief era of cosmic inflation, tiny quantum fluctuations grew to cosmic proportions. In the earliest fraction of a second after the Big Bang, space expanded at an extraordinary rate, stretching minute energy variations across vast distances. These quantum ripples became the seeds from which all galaxies and clusters eventually formed. Inflation linked the smallest scales of quantum physics to the grand structure of the universe, revealing a deep connection between the microscopic and the cosmic. Cosmic dust grains serve as the foundation for stars and planets. Composed of elements such as carbon, silicon, and metals, these tiny particles drift through interstellar space and gather within cold clouds of gas. Dust helps these clouds cool, allowing gravity to pull material together and ignite new stars. Around young stars, dust grains collide and stick, forming disks that can give rise to planets, moons, and asteroids. These microscopic grains also host complex chemical reactions, creating molecules essential for life. Though small, cosmic dust is central to the universe's creative processes. Light years provide a way to measure distances far beyond everyday experience. A single light year represents the distance light travels in 1 year, roughly 10 trillion kilometers. This unit allows astronomers to describe the immense scales separating stars, galaxies, and cosmic structures. Using light years reminds us just how vast the universe truly is and how long light has journeyed to reach our eyes. Using light years, astronomers can clearly express the immense distances separating stars, galaxies, and distant cosmic structures, helping us comprehend the true scale of the universe. A light year represents the distance light travels in a single year, linking space and time into one elegant measure. For example, the nearest star beyond our Sun lies more than 4 light-years away, meaning its light began its journey toward Earth over 4 years ago. Each distant object we observe is also a glimpse into the past. Light years transform the vast emptiness of space into a timeline, allowing us to visualize both distance and cosmic history through the steady journey of light. The universe's oldest light carries a temperature only a few degrees above absolute zero. This ancient glow, known as the cosmic microwave background radiation, fills all of space with a faint warmth of about 2.7 degrees above absolute zero. It is the cooled remnant of the universe's early, intensely hot state, stretched and chilled as space expanded over billions of years. Though nearly uniform, this radiation contains tiny temperature variations that became the seeds of galaxies and cosmic structures. Its cold, silent presence reflects the universe's transformation from a fiery beginning into the vast, calm cosmos we observe today. Cosmic ray showers continually cascade through Earth's atmosphere. When high-energy particles traveling near the speed of light strike atmospheric atoms, they trigger chains of secondary particles known as air showers. These cascades spread through the atmosphere and sometimes reach Earth's surface, where they are detected by instruments around the globe. Studying cosmic ray showers reveals information about powerful cosmic events such as supernova explosions and black hole jets. These invisible visitors also interact with atmospheric chemistry and may subtly influence climate processes. Their constant arrival reminds us that Earth exists within an active and energetic cosmic environment. Cosmic voids quietly influence the movement and growth of galaxies around them. These vast regions, nearly empty of matter, exert subtle gravitational effects that push surrounding material outward. This influence shapes how galaxies cluster and flow along filaments of the cosmic web. Voids help define the large-scale structure of the universe, guiding matter into complex patterns across enormous distances. By studying these empty expanses, astronomers gain insight into dark energy, matter distribution, and the forces shaping cosmic evolution. Though they appear barren, voids play an essential role in the universe's dynamic balance. Jets launched from black holes actively sculpt their host galaxies. At the centers of many galaxies lie supermassive black holes capable of producing powerful jets of charged particles moving near the speed of light. These jets can stretch millions of light-years into space, heating surrounding gas and pushing material outward. By regulating star formation and redistributing matter, black hole jets profoundly influence galactic growth and structure. Observing these energetic outflows reveals the intimate relationship between black holes and galaxies, highlighting how extreme objects shape the universe on grand scales. The first galaxies emerged during an era known as cosmic dawn. After hundreds of millions of years of darkness following the Big Bang, gravity pulled primordial gas into the first luminous structures. These early galaxies ignited massive stars whose intense ultraviolet light transformed the surrounding universe. Their radiation initiated reionization, altering the cosmic environment and ending the long cosmic dark ages. This period marked the universe's transition from silence to light. Studying cosmic dawn reveals how simple beginnings evolved into the rich complexity of galaxies and structures that fill the cosmos today. The universe's oldest light fills space with remarkable uniformity. The cosmic microwave background radiation bathes the entire universe in a faint, nearly even glow that dates back almost 14 billion years. Its temperature varies by only tiny fractions of a degree across the sky, reflecting the early universe's smoothness before gravity amplified small fluctuations into galaxies and clusters. This ancient light surrounds us everywhere, acting as a cosmic backdrop and a direct connection to the universe's infancy. It stands as a silent witness to the moment when space first became transparent. Measuring the ages of galaxies allows scientists to chart the universe's long history. By studying light that has traveled billions of years to reach us, astronomers effectively look back through time. Spectral signatures within this light reveal the ages of stars and the periods when galaxies formed and evolved. This cosmic archaeology helps reconstruct the timeline of star formation, chemical enrichment, and galactic growth. Together with other observations, these measurements paint a detailed picture of how the universe matured from its earliest moments into the structured cosmos we observe today. Cosmic evolution describes the continuous transformation of the universe across billions of years. From the intense heat of the Big Bang to the formation of stars, galaxies, and planets, everything in the cosmos is shaped by change. Matter and energy interact through fundamental forces, gradually building complex structures from simple beginnings. Galaxies evolve, stars are born and die, and new elements spread through space. Understanding cosmic evolution provides perspective on humanity's place within a universe that is constantly unfolding and reshaping itself over immense spans of time. Cosmic variance reminds us that we observe only one universe. Because astronomers have access to a single cosmic realization, measurements of large-scale patterns carry unavoidable uncertainties. Features seen in galaxy distributions or background radiation may partly result from random chance rather than universal laws. This limitation challenges scientists to refine models and carefully interpret data. Cosmic variance highlights both the power and the boundaries of cosmology, reminding us that our view of the universe is unique and incomplete. Cosmic rays interact with the solar wind flowing outward from the sun. This steady stream of charged particles influences how many cosmic rays reach Earth, modulating their intensity over time. Changes in solar activity alter this interaction, affecting radiation levels in the upper atmosphere and contributing to space weather. Understanding this relationship is vital for protecting technology, satellites, and astronauts from radiation exposure. It also reveals how our Sun acts as a mediator between Earth and the wider cosmos. Magnetic fields stretch across entire galaxies, quietly shaping their evolution. Though invisible, these fields guide charged particles, influence gas motion, and affect star formation processes. Spanning thousands of light-years, galactic magnetic fields intertwine with cosmic rays and plasma, adding complexity to galactic dynamics. Despite their relative weakness, their immense scale allows them to play a significant role in how galaxies grow, maintain structure, and interact with their surroundings over cosmic time. Reionization transformed the universe into a transparent realm for ultraviolet light. In its early stages, neutral hydrogen gas absorbed much of the radiation traveling through space, keeping the universe dark and opaque. The first stars and galaxies emitted powerful ultraviolet light that ionized this hydrogen, stripping away electrons and clearing the cosmic fog. This process allowed light to move freely across vast distances, permanently altering the universe's appearance. Reionization marked a crucial turning point, opening the cosmos to visibility and shaping the luminous universe we observe today. This transition fundamentally reshaped the universe's appearance, allowing complex cosmic structures to emerge and endure. By clearing away the dense fog of neutral hydrogen, reionization opened space to light, enabling galaxies, clusters, and filaments to become visible across vast distances. Studying this transformative era offers crucial insight into the universe's first luminous sources and the physical processes that lifted the cosmic haze, revealing how the universe evolved from obscurity into clarity. Cosmic dawn marked the end of the universe's long, dark, and opaque childhood. During this pivotal era, the cosmos shifted from a cold, lightless state into one filled with the first glimmers of illumination. Before cosmic dawn, neutral hydrogen absorbed nearly all light, keeping the universe dim and impenetrable. The formation of the first stars and galaxies introduced intense radiation that ionized this hydrogen, slowly clearing the fog. This gentle awakening transformed the universe into a transparent expanse where light could travel freely. Exploring cosmic dawn helps astronomers understand when and how the universe first began to shine, setting the stage for all cosmic structure that followed. Cosmic strings, if they exist, could reveal deep secrets of fundamental physics. These hypothetical structures are thought to be ultra-thin, immensely dense defects in space-time formed during the universe's earliest phase transitions. Stretching potentially across vast cosmic distances, cosmic strings could distort space, influence gravitational fields, and generate detectable gravitational waves. Discovering them would provide extraordinary insight into the unification of forces and the nature of space-time itself. Though no direct evidence has yet been found, cosmic strings remain a compelling possibility that could bridge quantum physics and cosmology. Inflation explains why the universe appears smooth and uniform on the largest scales. According to inflationary theory, the universe underwent an extremely brief yet dramatic period of exponential expansion shortly after the Big Bang. This rapid stretching smoothed out irregularities and spread tiny quantum fluctuations across immense distances. As a result, the universe looks remarkably similar in every direction. These microscopic fluctuations later grew into galaxies and cosmic structures under gravity's influence. Inflation resolves several long-standing cosmic puzzles and remains a cornerstone of modern cosmology, connecting the smallest quantum scales to the vast architecture of the universe. Photons from the Big Bang carry messages from the universe's birth. Released nearly 14 billion years ago, these ancient particles of light have traveled uninterrupted through space, forming the cosmic microwave background radiation. This faint glow fills the universe and encodes information about its earliest moments, composition, and evolution. By studying these primordial photons, scientists uncover clues about inflation, matter distribution, and the universe's origin itself. They serve as timeless messengers, linking the present cosmos to its fiery beginning. Cosmic rays were first discovered more than a century ago. In the early 20th century, scientists detected mysterious radiation penetrating Earth's atmosphere. Experiments by Victor Hess revealed that this radiation intensified with altitude, proving its extraterrestrial origin. These particles, mostly protons and atomic nuclei, travel at nearly the speed of light and constantly bombard Earth. Today, cosmic rays continue to fascinate researchers, offering insights into violent cosmic events such as supernovae and black hole jets. Their discovery marked the beginning of cosmic ray physics, connecting Earth directly to energetic processes unfolding across the universe. Cosmic horizons define how far we can see into space and time. Because the universe has a finite age of about 13.8 billion years, light from beyond a certain distance has not yet reached us. This boundary, known as the cosmic horizon, marks the edge of the observable universe. Beyond it may lie vast realms filled with galaxies and phenomena forever hidden from view. As time passes, the horizon slowly expands, revealing new regions. Yet due to ongoing cosmic expansion, some areas may remain permanently unreachable. The cosmic horizon reminds us that the universe extends far beyond what we can observe. The cosmic microwave background preserves a snapshot of the young universe. This faint, nearly uniform radiation originated when the universe was about 380,000 years old, after it cooled enough for photons to travel freely. It captures the universe at a moment when matter and light first decoupled. Subtle temperature variations within this glow reflect tiny density differences that later evolved into galaxies and clusters. Detailed studies of the cosmic microwave background provide precise measurements of the universe's age, composition, and structure, making it one of cosmology's most powerful tools. Polarization patterns in ancient light reveal the universe's earliest moments. Beyond temperature variations, the cosmic microwave background also shows polarization, a subtle alignment of light waves. These patterns contain information about primordial gravitational waves and early density fluctuations. By analyzing them, scientists test theories of inflation and explore how quantum fluctuations evolved into large-scale cosmic structures. Polarization offers a rare and delicate window into the physics of the Big Bang and the forces shaping the universe's birth. Cosmic filaments contain much of the universe's ordinary matter. Galaxies are not scattered randomly but are woven into vast filaments composed of dark matter and baryonic matter, including gas and dust. These immense structures stretch millions of light-years across space, forming the backbone of the cosmic web. Much of the universe's normal matter resides in hot, diffuse gas within these filaments, often difficult to detect. Understanding them reveals how matter flows through the cosmos and how galaxies grow within this grand interconnected network. Jets launched from black holes can stretch across millions of light-years. Supermassive black holes at galactic centers sometimes eject narrow beams of charged particles traveling near light speed. These colossal jets can influence regions far beyond their host galaxies, heating surrounding gas and regulating star formation. By shaping the intergalactic medium, they play a crucial role in galaxy evolution. Observing these jets reveals the immense power of black holes and their far-reaching impact on cosmic environments. Inflation left subtle fingerprints on the ancient light we observe today. During the universe's brief inflationary phase, quantum fluctuations were stretched to cosmic scales, imprinting patterns into the fabric of space-time. These imprints remain encoded in the cosmic microwave background as delicate variations in temperature and polarization. By studying these faint signals, scientists probe the universe's earliest instance and the physics governing its rapid expansion. Inflation's legacy unites the quantum and cosmic realms into a single, elegant story. Cosmic rays may subtly influence Earth's cloud formation. When cosmic rays enter Earth's atmosphere, they ionize molecules, producing charged particles that can act as seeds for cloud droplets. Clouds affect climate by reflecting sunlight and trapping heat. While the extent of this influence remains debated, the possibility highlights a delicate link between distant cosmic events and Earth's climate system. It suggests that processes unfolding across the universe may quietly affect conditions on our own planet. Galaxies move along paths shaped by cosmic filaments. Rather than drifting randomly, galaxies flow along gravitational channels formed by the cosmic web's filaments of dark matter and gas. These invisible currents guide galaxies toward dense clusters and away from vast voids. Over billions of years, this motion influences galaxy interactions, mergers, and evolution. Understanding these flows helps astronomers map the universe's large-scale structure and reveals the deep interconnectedness of matter across cosmic distances. Mapping these vast cosmic highways allows astronomers to better understand the invisible forces shaping the universe's grand architecture and guiding the motion of its countless components. By tracing how galaxies flow along these immense structures, scientists uncover the hidden gravitational patterns that sculpt the cosmos over billions of years, revealing the deep order beneath its apparent immensity. Neutrinos offer rare and delicate clues about the universe's very first moments. These tiny, nearly massless particles were produced in extraordinary numbers during the earliest instance after the Big Bang. They separated from ordinary matter just seconds into cosmic history and have been streaming freely through space ever since, barely interacting with anything along their journey. Though extraordinarily difficult to detect, relic neutrinos carry priceless information about the universe's infancy, the nature of fundamental particles, and interactions occurring at energies far beyond our reach. By studying them, scientists gain access to conditions that no telescope can directly observe, opening a subtle yet profound window into the origin of the cosmos and the laws that govern it. And now, the vastness of the universe begins to gently recede behind your thoughts. You have drifted through countless quiet wonders, from the radiant birth of stars to the hushed silhouettes of ancient galaxies. You have traced the invisible threads of dark matter, listened to the faint echoes of cosmic background light, and glided through stellar nurseries where new suns slowly awaken. You have traveled along glowing spiral arms and glimpsed the universe's heart, softly illuminated across distances beyond imagination. You are part of this cosmic story, not merely an observer looking outward, but a participant woven into the fabric of space and time itself. The atoms within your body were forged in the blazing cores of long-dead stars. The air you breathe carries the subtle imprint of distant explosions that once reshaped entire galaxies. Everything within you shares a common ancestry with the universe, born from the same primordial matter that now drifts between stars and flows through galaxies. As you rest tonight, the cosmos continues its quiet unfolding. Stars are forming in distant clouds. Light continues its endless journey across space. Galaxies turn in slow, graceful dances, bound together in silent harmony. And here you are, a small, warm presence within this vast, luminous sea, gently floating among the stars. Thank you for traveling through the universe tonight. May your sleep be deep, your thoughts peaceful, and your dreams soft and starlit. Good night. Milky Way.